Hello, thanks for having me. Good morning. Yeah, so we have this great wealth of lunar samples in the form of meteorites, but we're ultimately constrained in the amount of information that we can glean from them just because we don't know the full context of where they were on the moon. And yeah, it's something that we're trying to work on with this. Yeah, so basically any measurement you're going to take is going to be x plus or minus y. You can think of this as a probability density function where you have one PDF for the measurement that you take in the lab of your sample and one that you take from remote sensing. In this case, we're using Lunar Prospector's gamma ray spectrometer, but the concept generalizes to most things. So what was done in the past was selecting an interval of this PDF on both the sample and the remote sensing measurement out to 1 sigma or 2 sigma, some interval that you choose, and seeing if those intervals overlap. If they, in this case, at 1 sigma, they don't overlap, but with 2, if you extend it out, you see that they do overlap. And if they overlap in all elements in an elemental composition like you get from the LPGRS, you would say that this area of the moon agrees well with what we've seen in the sample. Skip a bunch. But one thing that this produces 2 issues that we run into. One is that it introduces this kind of fiddly parameter trying to decide how wide of an interval to take in order to try to get a match. You can, if you set it too small, you select nothing. If you set it too big, you select kind of a uselessly large area of the moon and you don't really get much constrainment at all. The other thing you can see here is that this is only producing like a hard binary yes, no, this area agrees or doesn't agree. We wanted to try to introduce some kind of relative notion of this area. They both have some similarity, but this area matches better than another. So happened again. So instead of trying to look at the interval overlap, whether or not the interval overlaps or doesn't overlap, we look at the area covered by both PDFs. Yeah, basically just integrating over the minimum of the 2 PDFs. So in this example, basically, so the nice property of this is that if you have if your meteorite sample perfectly matches a remote sensing measurement, this area will be 1, and as they start to diverge in similarity, the overlap coefficient will start getting closer and closer to 0. What we do to handle multiple elements here is we just multiply them together. This was a decision made so that if a region of the moon matches perfectly in a whole bunch of elements, but in a different element has a terrible match, it should still probably rank lower than something that matches pretty well in all elements. Another thing worth pointing out is that this number doesn't really have any statistical or physical meaning. Like if this number were twice as high, it wouldn't necessarily mean that it's twice as likely. This is just kind of a relative notion to compare between different areas. So this was one of our So we ran this on 9 samples from Apollo and Luna, just to make sure that we weren't producing nonsense. And Apollo 14 showed really great constrainment. This was something that posed some issues with the previous method because of the very high thorium content. You had to extend the interval out very wide in order for it to match anything at all. So these areas that match are fairly low because the thorium is so high. The overlap coefficients tend to be pretty low, but compared to the rest of the moon, they are by far the highest. So it still produces a nice highlight and helps produce some good constrainment. We then ran it on 25 meteorite samples using thorium, titanium, and iron. And you can see that there's good constrainment both for the NWA and LAP groups. The LAP groups show very strong correlation between one another, which makes sense. You put the same numbers in, you should get the same areas of the map lighting up. One thing that it does struggle with a little bit at the moment is feldspathic samples. Because, like I mentioned, this is iron, titanium, and thorium, so it can help differentiate the basalts, but might not be as helpful with the feldspathic sites. The LPGRS does have data for magnesium and calcium, but they are quite noisy, so they don't really contribute all that much for differentiating the feldspathic sites. This is something that I'm excited to see the results from the Denori GRS in the future. Yeah, so one thing that I would love to see in the future is higher spatial resolution for these things so that we can try to narrow things down even further. Trying to get tighter bounds on magnesium and calcium samples. One final thing I want to point out with this is that this is a fairly general method. So as long as you have X plus or minus Y in a comparable axis for both your meteorite sample and remote sensing, you should be able to apply this fairly easily. Ultimately, the impetus for this project was to have a tool that people could use. So all the code is up on GitHub. For the less technologically inclined, I've just uploaded all of the results to the website as well. Yeah, that's pretty much sums it all up. Thank you very much.